So according to what we learned in Chapter 4, what is our process? How would I multiply out the polynomial x minus 12 times the polynomial x minus 2? What do I do? Distribute. And since we have a binomial times a binomial, what exactly am I distributing here?
The x and the x.
Okay. The x and the x, the x and the negative 2, negative 12 and x, and negative 12 and negative 2. Right. So what I end up with is a product, actually four different products of terms. If we wanted to, we could represent this in a little chart. We did a little bit of this before. Right? Where on the one hand, I have x and negative 12, and on the other hand I have x and negative 2. And when I multiply, I should get a product for each one of these four different possibilities. What is x times x? Better known as x squared. And then negative 12 times x? There's not much to do with that. That's just negative 12x. Negative 2 times x likewise. And negative 2 times negative 12? Yeah, positive 24. So that when I multiply this all out, I will get a term that has just x squared in it, a term that just is plus 24, but then I'll also get a pair of terms coming from this box and that box, the negative 12x and the negative 2x, and when we add those two together, what do we end up with? What is negative 12x plus negative 2x? Negative 14x. Combining the like terms by adding their coefficients. So we figured out in Chapter 4, at the end of Chapter 4, how to multiply polynomials out. And that was the guiding principle, is that the distributive property tells us that every term from one of them has to multiply with every term from the other. And then once we have all those results, we can simplify them out to get our answer. Where we would like to be able to go is we would like to be able to take expressions like x squared minus 14x plus 24, like this quadratic that we have down here at the bottom. And we'd like to figure out how to do the following. Here's our ultimate goal. Our ultimate goal is to be able to solve. And when I'm using the word solve, I'm talking about equations here and not just expressions. And the kinds of equations that we want to be able to solve are equations that have quadratic expressions in them. So equations like, say, x squared minus 14x plus 24 is equal to 0. Right? Our ultimate goal is to be able to solve an equation that has one of these second powers of x in it. Right now, we don't really have any tools that will let us do this. Because there's no way for us to combine like terms on the left-hand side to get the two terms that have the x's in them together, because one of them is an x squared, the other one is an x to the first. So there's nothing that we can do up to this point using just sort of straight-up methods of solving equations in order to address an equation like that. There's nothing on the table for that. So the solution to that is, what if we could do the process that's on the left-hand side of the board here? What if we could do that process backwards? So we could do this backwards. And what that would look like is the following. Say we start with an equation like x squared minus 14x plus 24 is equal to 0, like the one that's at the top of the board here. If I happened to know that x squared minus 14x plus 24 were the same thing as x minus 12 times x minus 2, so reversing the operation we had on the left-hand side of the board, then when I look at this equation that's right here, what I see is one expression times another expression, x minus 12 times x minus 2. And when I multiply those two expressions together, the result becomes 0. That's what the right-hand side of this equation is telling me. And from here we can make an observation and this is the most important observation for this whole process. The observation is, if I multiply two numbers and the result is 0, then what do I know for sure must have been the case with those original numbers? If two numbers multiply together to give us 0, one of those original numbers must have been 0. Right? There's no other way to get a product of 0 unless one of your factors was 0. Right? That 0 is a special number like that. And it gives us a property that we call the zero factor property. Zero factor property. If two quantities multiply together to give us 0, that must mean that one of the original quantities was itself equal to 0. And this only works for the number 0, by the way. If the right-hand side of this equation is anything else, then we can't do this the same way. But if the right-hand side of this equation is 0, that tells me that either x minus 12 must have been 0, or that x minus 2 must have been 0. There's no other possible way. Right? If I multiply two things together and the answer is 0, then one of those original things must have been 0. That's the zero factor property. What's the benefit of this? Well, how do I solve the equation x minus 12 is equal to 0? What we've ended up with here are two equations that are much simpler than the ones that we started out with. And we know how to solve them. We knew how to solve them weeks ago. Right? Add 12 to both sides to get x equals 12 on the one hand. Likewise for x minus 2 equals 0. Add 2 to both sides to get x equals 2. So this is the power of the techniques that we're about to dive into here. The power of the techniques that we're going to develop over the next couple of classes is that it's going to let us solve equations like this by factoring the left-hand side. In other words, doing the process that we did over here on the left side of the board, where we multiplied out, and do that process in reverse, so that we can discover what multiplies together to give us this expression. And as soon as we do that, and we have a 0 on the other side of the equation, the zero factor property lets us break those two factors apart and solve each one of these much simpler equations separately. And what we end up with here, in this example at least, is an equation that has two different solutions for it. X equals 12 will make this equation true. X equals 2 will also make this equation true. And our other methods of solving equations that we had before would never have led us to more than one possible answer. These methods can, and that's what makes them different.